So let's start with the other application, which is resource allocation game. Models allocating some basically indefinitely divisible resource between several participants. As you can imagine, there are extremely many such applications, bandwidth and so on. But we are going to look at a relatively simple but important model, which introduces heterogeneous values. And the idea is that every player can have an own value function, so not necessarily that every player values some capacity to the same extent as every other player. That's the idea of this value being heterogeneous. And the game consists of the following. So you have some number of players, the capacity which we divide between players. It's not like capacity that we look at some flow which needs to be carried through the capacity. Maybe we will, but the model itself just divides that. So it can be maybe better formulated as a bandit. You divide some indefinitely divisible real number between several players. It can be up to an extent, it can be even money. But no, money is not a good idea because paying for money would be not what we need. So we divide some resource between players, and that's what we call capacity. Yeah, just don't get confused by these names. We divide something. You don't know how players will use it. For example, a good example can be band. And player i's value is concave, strictly increasing, and also continuous differentiable. So C1 means that the function is differentiable and the derivative is a continuous function. We also assume to be able to define in the future what happens if every player bit 0, which will still define what it means. We have not mentioned bits yet. We need to have this edge case that the value of 0 is always 0. It's not something the book does, but we do it to be able to define the social welfare when every player beats 0. The book does not look at this edge case. Now, again, it's not crucial. Now, the outcome is some division of the capacity, so the sum of those x's. See, they are all non-negative. Unless all the bits are 0, in which case we are allowed to just not use the capacity. But otherwise, we just need to divide the capacity between players without the social welfare is utilitarian. So we just want socially to optimize the total value of the players. Please note that that's not total utility. So it's not exactly like we defined a utilitarian utility before, where the utilitarian social welfare was just the sum of the utilities. Here it's the sum of the values, whereas the utilities, so the functions which the players personally want to optimize, they are a bit different. So we just want to optimize the total value. And the proportional sharing mechanism receives the bit. The bits are basically the strategies. So the player decides how to bid. The player does not provide a function. It cannot. There is no option to provide a function in this mechanism, in this game. When I tell mechanism in a game, the player just provides a number, and the mechanism allocates each player the ratio of her bit relatively to the total bit of this capacity, unless, of course, everyone bits 0, and that in that case it's not defined. The sum of the bits is 0, so the denominator would be 0. So in that case, we just assume that everyone gets 0. Therefore, I allowed for the outcome of something else which does not use the whole capacity when everyone bits 0. And then what player actually obtained as her utility is defined as the value of this outcome minus the payment, which is just a bit. So a player just pays a bit and therefore obtains the value minus the bit. In particular, if all the players bid 0 in this edge case, it's not an important edge case even. It's just that I think the book does not cover that, and I just wanted to cover it so that you don't get confused. I want kind of to make it easier for you. So therefore, I emphasize that. And in the case everyone bit 0, we said that the outcome will be 0, and then the value of the outcome is defined to be 0, and therefore it's going to be 0 minus 0, 0. So the book just claims that utility should be defined as 0. It's also important to define the social welfare. In this case, it's important to define, to mention that the outcome may be less in total than C in some case when everyone is 0. So it's important just to make it kind of clear, including the edge case. So basically, we define the game. So the strategies are the bits, define how the capacity is divided, and the player's utility is the value for the player of that outcome xi minus the payment bi, whereas the social welfare is not the sum of the utilities, but rather the sum of the values. So the difference is the sum of the bits. It's important to take note. And the conditions on V, which we said that V is continuous differentiable concave and strictly increasing, implies that also UI is continuously differentiable and strictly concave in BI when the rest are fixed. Of course, assuming that the rest is the positive sum, so that we don't look at the edge case and we just use the formula. And one can prove that every Nash equilibrium has the same social welfare. However, no efficiency is guaranteed. Actually, it's always true that the game, or excuse me, there are games, not always. There are games, because there are games when it's going to be. There are games where this unique social welfare of the Nash equilibrium is suboptimal. For example, when you have a game, the value of player 1 is twice the outcome, what she gets, and the value of every other player is just the outcome, what she gets. One moment. Here, the unit of optimum is, of course, just to, when you want to optimize the sum of the values, we just want to give everyone to player 1. However, this is never an equilibrium. It is the location. In order for the other players to get 0, they need to beat 0, and player 1, of course, in order to get something else, needs to be something positive. Now, however, this is never an equilibrium, since player 1 would still get everything when beating anything else which is positive. And therefore, by beating something positive but smaller, strictly smaller than B1, player 1 would have to pay less and thereby would strictly increase her utility. So that's not an equilibrium. And for any positive beat, you can beat something positive smaller, which is smaller than that. So we may need to go to some epsilon equilibrium here. If you want to have an optimum equilibrium. But that's beyond what we are talking about now. So we've now proven that the only optimum social welfare allocation is not an equilibrium. Price of stability and the price of anarchy is the same here, as we said. We proved it for price of stability, but actually they are both same here. Actually, no, wait a second. We prove that every optimum allocation is that, and that's not an equilibrium. So there is no equilibrium which is optimum. Yeah, both price of stability and price of anarchy is proof. They are greater than 1. And as I said, it can be proven that they are all the same. Equilibria have always the same social value. The intuition for why that's the case is that the player 1 has too much market power. So when the rest don't bid anything, player 1 can play with what she bids, and she can always bid a bit less and improve what is formally improve, strictly improve utility. And you can also look at another case of a similar thing. So when B1 is much larger than the others, some of the other bids, so that low in BI would be strictly profitable. Indeed, in the general case, it will strictly lower the amount of the share of that player and therefore the value, but it will not lower that as much as the payment has been decreased. Therefore, it will be profitable less to do it at every equilibrium, at every optimum profile, so no optimum profile will be an equilibrium. And formally what we do now to show that we actually start from an equilibrium, unlike what we did at the start with optimum profile, we start from an equilibrium and prove that it cannot be an optimum profile. So look at an equilibrium. You know just the total bit, sum of the bit by capital B, and then we prove that for each utility function, which is excuse me. Use something which we'll probably prove at the tutorial, or I'll give it for you to prove at home. It's an extract from the book. That because of what we know about this, about the value function, the utility function, which is simply the value function minus the value, the bit, is also continuous differential. And when I fix the bits of the others, the utility function is also strictly concave in the bits of the bit of this player. And of course, it's not only for bit 1, it's player 1, it's in general. So the utility function of player I is strictly concave in BI. Let me fix that. I now have compiled that, and let's need some time to the change goes through and becomes visible for everyone in the slide. So since we started with an equilibrium, it means that every player reacts optimally to what the others do. Now, the derivative is therefore 0, and since we know that at least 2 players have to play positively in equilibrium, that's something we'll prove later. It's also an exercise at the end of the chapter in the book. Then, for some neighborhood of that equilibrium, you can just use the formula of this ratio between BI and sum of the others, because at least 2 players play positive. And therefore, using the formula and differentiating and equalizing the derivative with 0, we obtain this condition. 2b capital minus capital B minus B1 divided by B squared is 1. Similarly, for any player with index greater than 1, so for every player other than player 1, I remind that player 1 had this utility 2x1, and the other have another utility, just xi. For any other player, we get another condition. Well, it's exactly like without the 2, because actually, yes, the utility function and the value function, therefore the utility function. Okay, I won't now go into why. That's quite simple, because you have like a derivative which is something minus 1, and that's something, the derivative of vi xi differs exactly by the factor of 2, but that's something you can do yourself. And together those equations, so this equation for player 1 and equation for every other player, by simple algebraic manipulation, which you can look up at the book if you want, or do yourself, apply that in an equilibrium. B1 is about a bit more than half of the total sum of them. Therefore, for large enough n, of course, this can be done formally with this estimation. For large enough n, what B1 gets is about a bit more, but about half of the capacity. So her share is about half, which results in the social welfare of about 3/2. Whereas the optimum social welfare, when player 1 gets everything, is of course 2. Right? Value of player 1 is 2, value of the others will be 0, so the optimum social welfare is 2. And therefore, if you divide define the price of anarchy or stability, true for every equilibrium here, as the ratio between what can be achieved and what the equilibrium achieves, then it's going to be 2 divided by 3 over 2. It's going to be 4 divided by 3. Greater than 1 in particular, suboptimal. And now let us look, we'll still get back to the example, but let us now look at the general idea of how measuring equilibrium efficiency can serve as a guide for mechanism design. And that's actually very interesting because that's a very large active domain which is being studied all the time, mechanism design. It's one of the areas where game theory actually is extremely useful. So there are many cases where the simple homo economicus, which game theory tends to assume, not only, but tends to assume that people just have this simple utility function, especially nice if it's according to the von Neumann-Morgenstern assumption, that's what you do. And then, according to those simple assumptions, game theory solves its problems, and that's always not the case. That the assumptions, often the assumptions do not work because they simply don't apply in many cases. Our utilities are sometimes not what von Neumann-Morgenstern assumed. We often are not rational and so on. But in some economical cases, which, for example, include auctions, many auctions, they have been extremely useful and indeed practical, not only theoretical, but also practical, interesting domains where mechanism design has been interesting, successful. So designing a mechanism basically means designing a game that will make players do what we want. Unlike a game where you have something, some interaction given to you, and you analyze what's happening there, like we've done till now. For example, we are given this mechanism for dividing the bandwidth, and we just see, okay, the national equilibrium is this, or they are this, and the optimum social welfare achieves this profile, and so on. That's analyzing a game or a mechanism. Game is a mechanism. Design the mechanism, and the domain is called mechanism design. That's basically the dual problem. You ask me, given that I know how players probably behave, for example, I assume that they behave according to the national equilibrium, what shall I tell them? What are the rules? What are the laws? What are the rules of the auction, for example, of the elections, or something else that will motivate them to behave in a way I want? For example, in an auction, what will motivate the players to bid exactly the amount they value that with which they value the self item. So that's mechanism design. That's a very important topic, and as I said, that's something which is actively studied. And what we're going to look now is how we can guide mechanism design by efficiency consideration, and that's going to be like a particular approach to that. So that's not going to be the general mechanism design, but there are many works on here. So let's go. So till now we look just a fixed game and analyze the equilibrium and the efficiency. But when we see that the equilibria which exist are very bad, we just need to change that. Now we sometimes may want and may be able to dictate what to do, but sometimes we are not able to dictate which equilibrium to choose, or even if they're all bad, we are not able just to tell people do that, even if that's not what you prefer. If they are not able to do that, which is often the case in society, online, and so on, mechanism design actually looks for how can we find an interaction which possesses better equilibrium. So, for example, in a class of mechanisms, so all interactions when you don't require payment without money, please find the information place, and let's say the place, everyone flag provides one single number about the preference. Then please find within this class of mechanism which guarantees the base price of 100%. Now another question is, given a game, when you are given a game already, it's not like from scratch. And you can just change, you can adjust the game so that the equilibrium will be influenced accordingly. Which adjustment shall you carry over? Excuse me, which adjustment shall you undertake in order to optimize the situation so that the price of anarchy is as close as possible to 1? And the problems we are looking at with the realm of this equilibrium efficiency measures guiding mechanism design, they are a bit different from the typical mechanism design problems. For example, we can consider here not like when we just reveal what we are. So direct revelation means that you just reveal exactly everything about yourself. For example, if I buy an item at the auction, I can reveal exactly how much I value the item. We typically want something which is direct revelation, and when revealing my true value is a dominant strategy, this weakly dominant. Now, in proportional sharing, the example we just looked at, that's actually not a direct revelation mechanism because you don't reveal your value function. You just reveal a number. You just give a bit. Now, also another thing is that mechanisms, if we look at, they're often mechanisms when we don't have the control to do something, rather than like in the private int. So in a classical mechanism like an auction, you just select into how much each player wants the item. And therefore you just want to motivate them to give you the true value. But in selfish routing, for example, you elect the control. You're not able to tell people how to go. You know what they want. Let's say that it's kind of course, everyone values his time, each day differently, but still you're able to assume that you know what they want. But you don't know, you're not able to control what they do. And that's exactly what you are doing here. You just need a mechanism such that despite that you don't have the control, you motivate them to do something you want. And also, you often look at it, as I said, adjusting a game rather than designing a new game from scratch. For example, let's look at our old friend, proportional sharing mechanism. So we saw in our example that the price hierarchy is at least 4 or 3, and it's possible in China to prove that the price of anarchy is always at least that. In the book, they apparently divide the ratio differently in the opposite way, like they divide the smaller by the larger. So they have the opposite value, like 3 or 4. So don't get confused with the book. That's always the problem, that people get confused with how they divide exactly how they define the prices of anarchy and stability, what they divide by what. And so we've seen that. So one of the mechanism problems we can think of is how can we motivate this to decrease the price of anarchy, to make it closer to 1. The question, of course, is among which mechanism are we choosing? If any mechanism is allowed, then the famous VCG, which we have not studied here, but that's a very classical mechanism, which exactly can achieve an optimum allocation. But the problem is that it has some practical hindrances which prevent us from using it all the time. The communication complexity would be very high. So there, every player would need to communicate the full valuation function to the mechanism, and also the other way around. So the allocation which the mechanism communicates to the players in proportional sharing can be basically communicate using one parameter. For example, look at the sum of the bits. So the value in this mechanism, the outcome, is simply the bit divided by p, when p is the sum of the bits divided by the known value of the total value. You just need to communicate the players what is the sum of the bits, and then they exactly know how much they make, how much of the shared resource the resource being shared, they may take. But in VCG, it's not the case. It's a kind of a hard. It's a very hard to use tool. It's a very efficient tool. It's an optimum tool, but it's hard to use. So if we adjust, if we change the problem to asking, or is there a mechanism with the communication complexity of proportional sharing, which has a smaller price of anarchy, then the answer is actually no. We can prove, we don't do it here now, but one can prove that the proportional sharing is optimum among such constraint mechanisms. And to wrap up what we've been doing today and the previous lecture, what we've been doing in this slide, we basically looked at efficiency solution concept. We looked why they're required. We defined them, the most famous price of anarchy and stability. We saw that given already those definitions, the exact definition depends on what we look at solution concept. And also on which solution we take. So, for example, there may be several Nash equilibria. We choose to work with Nash equilibria. It's still a question which equilibrium we take, which I remind you resulted in the fact that we looked at two options, price of anarchy and stability, and the social welfare, which we use. So we can talk about utilitarian social welfare, we can talk about egalitarian, and also in the utilitarian, I remind you to look at the maximum, for example, the utilitarian social welfare. Sometimes we don't look at the sum of the utilities, but rather the sum of the values. And so we define price of anarchy and stability. And then we look at some examples. So the first example is called non-atomic network routing, where players need to decide through which route they go, and we assume that there are infinitely many players, so that was actually modeled not as in some players, but as a flow. But the intuition was that it models infinitely many players, and we looked at this go example, which actually showed the price of anarchy of 403, which also can be proven. I think we do it in this course to be the actually worst price of anarchy in such networks, provided the functions, the capacities are fine. Otherwise, of course, the price of anarchy can be indefinitely large. Now, the Shapley network design game, that was another game where we choose which path we use, and the players just pay for those paths. It's a normal game already. You have a finite number of players, and they just choose which path to use and pay for the path. And we show that sometimes we can have a price of anarchy as large as harmonic. It can be shown, I think, to be general, but we just showed that for our example. Another important example is scheduling games, where price of anarchy was shown to be 1 for makespan and utilitarian social welfares. The makespan basically is the egalitarian. Let's look at the worst. The last fulfilled assignment, and the price of anarchy was 1 for fewer games, and for mixed extensions, we also considered the price of anarchy, and they were not 1, so then it was suboptimal. And also looked at resource allocation game with proportional sharing mechanisms, and we considered some examples which show that it can be actually always inefficient. In some cases, it can be inefficient. Such a game can be always inefficient. And then we talk in general about designing mechanisms, so designing a game or adjusting a game guided by the equilibrium efficiency. And again, we looked at this example of proportional sharing mechanism, example of such an approach. Okay, please Let me know if you have any questions, and goodbye.